Hello everyone, this is me Dr. Savitha M. I am now uploading the second video on corrosion and metal finishing. Here in this video, I will be discussing on the second part, that is factors influencing the rate of corrosion. Kindly find all the videos in the YouTube channel, My Intuition. Now again, just recapping, corrosion. What does corrosion means? Corrosion means it is the destruction or deterioration of the metal and thereby consequent loss of the metal due to the environment attack. Right now, the environment attack means the two regions which are involved, two factors that is involved is one is environment and another one is the metal. Right. So the factors affecting can be broadly classified into environment factors or metallic factors. Right now, environment factors means what are the factors in the environment, like pH, conductivity of the medium, temperature, all these. Or in the metallic factors means factors which is pertaining or which will be depending on the metallic properties. Right. First, let us go for the factors related to the metallic compounds, metal. Right now, first one is the nature of the metal. What metal you have chosen, that also decides the nature, I mean the rate of corrosion. Second one is relative area or size of anode to cathode, or ratio of anode to cathode. That means if you're taking two different metals, then if the size of the anodic region and the cathodic region are different, will it affect the rate of corrosion? The third one is nature of corrosion product. Corrosion will produce a corrosion product. This product, as we have discussed, we know that it will be deposited on the metal area, metal surface. How will the corrosion product affect the rate of corrosion? The next one is polarization of anode and cathodic regions. Okay, let me go one by one in detail. Nature of the metal. Now, what metal we have chosen, that also decides. For example, if you design everything, practically we know that if you are producing anything by iron, it undergoes corrosion. Let us assume we have designed everything by gold. We know that gold will not undergo corrosion, right? Because it has very high reduction potential. That's why gold does not, practically it may not be possible using preparing or designing everything with gold due to cost and all. But the fact is that the gold does not undergo corrosion. That's why we are making ornaments of gold, not iron. Because iron, if you make ornaments, within a few days only it will undergo corrosion and you'll be losing that. Right. So reduction potential of the metal decides the rate of corrosion. Right. So that means in general, if you make any design with the metal with higher reduction potential, it will not undergo corrosion easily. Similarly, if you design anything with a metal with a lower reduction potential, then it will be easily undergoing corrosion, because it has a higher tendency to get oxidized. Oxidation is nothing but corrosion. Right. If you prepare anything with the metal, sodium, potassium, magnesium, zinc and all, it will it will undergo corrosion within no time at all. Right. Next is the nature of the, under this only, sometimes it will not go, this concept of predicting the corrosion reaction depending on the reduction potential, sometimes it will not give correct results. We have discussed in previous video that you have to refer to galvanic series, because the reduction potential we are getting from electrochemical series. Some metals like aluminium, titanium, chromium and all, according to electrochemical series, it says that it undergoes corrosion very fast. But in reality, these metals do not undergo corrosion. This is because these metals, first initially they undergo corrosion. They will produce a protective layer, and later this protective layer itself acts as a barrier between the metal and the environment. Right? Therefore, it will further not undergo corrosion. But in general, if you have the reduction potential, or if you know the reduction potential of a metal, you can predict what is the nature of its corrosion, whether it is undergoing corrosion very fast or it is not undergoing corrosion very fast. Okay, so the metals with high reduction potential value have higher tendency, I mean lower tendency to undergo corrosion. Okay, similarly the metals with higher reduction potential will not undergo corrosion, like gold, silver. These are all having these are all metals with higher reduction potential, so they will not undergo corrosion that very fast. Okay, the next is, suppose you are designing something with two different metals. Avoid such cases, but whenever you cannot avoid, you are using two different metals, then out of the two, the difference in the reduction potential decides the rate of corrosion. That means E cell is equal to E cathode minus E anode. The higher the difference, the higher will be the potential. E cell also will be higher. Therefore, the rate of corrosion also will be higher, right? Next is relative size of anode and cathode regions. Now, when you are designing something with two different metals, then the if the area of anode is higher than or larger than the area of cathode, then the corrosion rate will be uh, lower, because it is the cathodic region. Moreover, cathode, the metal itself is not demanding electrons, but it is a region or it is a surface where the environment comes and asks for electron. Therefore, if the cathode regions is higher, then there will be larger demand for electrons, because since the area of cathode is large, it will be demanding for electrons. If the area of anode is small, that small area will have to satisfy the large demand of electrons. Therefore, if there is a larger demand, small supply area, in that case the anode will have to work more and again to supply or to satisfy the demand of electrons. In that case, the anode will be accelerating its reaction rate. Okay, its own reduction potential will have a certain value of liberating rate at which it will liberate electron. But if the anode area is small, if the demand of electron is more, then it will work so hard that it will be liberating electrons more beyond than its reduction potential itself. Therefore, if the anodic area is smaller than the cathode region, then reaction rate will be more, right? The electrons, at the on the other hand, if the anode area is large, right? Anode area is large means electrons are liberated. There are supply area is large. Cathode area is small. That means the accepting area is small. Therefore, there will be lesser demand of electrons. Okay. When there is lesser demand of electrons, automatically anode will reduce its rate, because if its electron are not accepted at the cathode, it will simply not liberate electrons. Only if there is a demand, it will liberate electron, right? Since it is not accepted at the same rate, it will reduce its rate. Therefore, if the anode area is larger than the cathode, corrosion rate decreases. At the same time, if the cathode area is larger than the anode, the corrosion reaction will be very high, right? And some examples is, suppose you have a tin coating on iron, right? If you see the reduction potential of tin and iron has a lower reduction potential than tin. Therefore, iron will be the anode and tin will be the cathode. Suppose you have a tin base and on which you are coating with the, I mean, if you have a iron base on which you are coating on uh, with the tin, right? And there's a small rupture in the coating. That means in that small area, iron is exposed. The entire area is tin, right? Tin is cathodic with respect to iron. Therefore, a small anode is exposed. There's a large cathodic area. Demanding area is large and the supply area is small. Therefore, corrosion reaction will be very fast. Okay. Uh, that is why broken um, tin coating on iron is always dangerous, right? For and another example is if there are iron bolts and nuts on copper vessels or boilers. If you have a copper container or a copper boiler which has iron and iron bolts and nuts made up of iron, then the corrosion reaction will be very fast because iron is anodic compared to copper. Copper, entire boiler is made up of copper, large cathodic area. Bolts and nuts are small area, small anode area. Supply region is very small. Therefore, iron will have to work so much or undergo oxidation very fast to supply the need of electron. Therefore, it is not a good demand, a good design. First of all, using two different metals itself is not a good option. Suppose sometimes we may not be able to avoid two different metals, then at least we have to keep a washer so that they are directly not in contact with one another, right? So you must have heard of using a non-conductive washers and all, right? Sometimes we have to we may not be able to use the washer also, and we have to design something where there are two different metals directly in contact. In that case, at least we have to design in such a way that the cathodic area is small compared to the anode area, right? Supply area is larger than the demanding area. When the demand is less, automatically the liberation or production of electrons or corrosion as a whole will reduce. Okay, so that means if you take the ratio of anodic area by cathodic area, and if that ratio is lesser than 1 means the anodic area should be smaller than the cathodic area, then the corrosion reaction will be very fast. On the other hand, if the anodic area ratio of anodic area to cathodic area is greater than 1, that means cathode area is lesser than the anode, then corrosion reaction will be slow. Okay, so that is the ratio of anodic to cathode. Okay, next is nature of the corrosion product. Corrosion product means what? It is the product of the corrosion or the oxide film, oxide product, metal oxide, which gets deposited on the starting from the cathode it starts, and later it will go on depositing on over the entire area, right? Now after a certain thickness of the oxide layer, initially corrosion goes on continuing, it goes on producing the corrosion product. The corrosion product goes on getting deposited on the metal surface. After a certain thickness of the corrosion product, then the further corrosion is decided by the nature of the corrosion product, right? And this is explained using a Pilling Bedworth rule, right? According to this rule, it states that if the corrosion product is non-porous and continuous, that means the base metal is completely surrounded by the corrosion product. Let us assume the base metal is completely surrounded, no parts of the base metal is exposed to environment. The moment the metal is not exposed to environment, it will not undergo corrosion, right? The corrosion product itself is acting as a barrier, right? It itself is blocking the environment entry to the or environment what contact with the base metal. In that case, corrosion rate reduces, it will go to, it will become very less, right? So such a type of corrosion control can be is possible when the corrosion product acts as a perfect barrier. That means there are no pores, there are no, it is very continuous, it is not stripped off anywhere, and it is of a certain thickness, right? So it will act as a perfect barrier, right? It will not allow the environment to enter. Then the corrosion rate of that base metal will reduce, right? On the other hand, if the corrosion product is uh, porous, that means if there are pores in that, if it is not stable, if it is if it is not uniform, right? In that case, the small pores acts as channels for the environment entry, and in that small channel environment entry will enter, and the ions will enter, and that small area where the environment can enter, that is the anode region, whereas the entire part is the cathode region. Again, small anode, large anode, cathode. right? Corrosion rate will increase. Therefore, see, the corrosion product acts as a perfect barrier if it is non-porous and continuous, and the corrosion rate will reduce. On the other hand, if the corrosion product is porous or discontinuous, or it is unstable, then it will not reduce the corrosion rate. It will rather increase the corrosion rate, right? So that is the nature of the corrosion product, right? All this is explained by Pilling Bedworth rule. Okay, the last one is polarization of anodic or cathodic region, right? These are all the factors related to metallic factors. Okay, as we know, the word polarization means creation of poles. Creation of poles means creation of positive and the negative area regions, right? In the anodic region, what happens? Corrosion reaction takes place. Metal ions are liberated, electrons are liberated, electrons go towards the cathodic region through the metal, whereas the metal ions diffuse from the anodic region towards the cathodic region. Just let us assume the metal ions which is formed or released at the anodic region is not going very fast towards the cathodic region, right? Or uh, some ions in the environment go near the cathodic region and accept electrons, right? When it accepts electrons, only then the second set of electrons will come, right? Let us assume if the ions in the environment is not going, um, I mean very slowly going near the cathode, what will happen? It is the electrons have already come, right? The electrons have already come. It is only waiting for the ions to accept it, so that the next set of electrons will come. Now the first set of electrons itself is not getting accepted. Automatically the second set gets delayed, right? So all the electrons already come near the cathodic region, and it will be waiting for the ions to accept. Therefore the cathode becomes negatively charged. At the same time, let us assume a condition where the metal ions are present at the anode, right? It is liberated at the anode, and these metal ions are not diffusing towards the cathode very fast. Then what happens? The cathode I mean at the anode region, all the positive ions will be staying near to the anode itself, and it looks positively charged, right? In both of the cases, whether anode is positively charged or cathode is negatively charged, in both of the case, the next reaction is becoming slow. That is, corrosion reaction slows down, right? So this creation of poles is called as polarization. Now polarization can happen either by due to the slow diffusion of electroactive species at the cathode region, or slow diffusion of the metal ions at the anode region, right? So when the polarization takes place, and whether it is anodic polarization or cathodic polarization, both will reduce the rate of corrosion, right? So the higher the polarization of the metal, either anodic or cathodic, it lowers the rate of corrosion. Okay, so next are the factors related to the environment. There are three factors in the syllabus. The first one is electrical conductivity, or pH of the medium, or temperature. First one is electrical conductivity. Conductivity means it is decided by the speed of ions. If the ions move very fast towards their respective regions, reactions will be fast. Corrosion reaction also is fast. Second one is the pH of the medium. pH of the medium means it gives you the idea about the presence of H plus ions in the medium. As we have discussed in the electrochemical theory of corrosion, that is the reactions of corrosion, we have come to know that when the medium contains H plus ions, liberation of hydrogen gas becomes easier, right? So at a lower pH, where the availability of H plus is more, lower pH means acidic region, where the availability of H plus ions are more, then liberation of hydrogen also becomes easier. Therefore corrosion reaction also will be faster, right? On the other hand, if the pH is high, then the corrosion reaction will be less slower. Okay, but there are some exceptions. Exceptions, like for example in the reactions of aluminium, zinc and all, they undergo higher corrosion or faster corrosion in alkaline medium, that is higher pH, right? But in general, lower the pH, higher is the rate of corrosion. Third one is temperature. We know that the any chemical reaction increases the rate of its rate with the increase in temperature, and so is the corrosion reaction also. As the temperature increases, corrosion rate also increases. So when the pH is lower, the corrosion rate is high. When the temperature is higher, the corrosion rate is also high. When the conductivity of the medium is increasing, the rate of corrosion is also higher. Right? So these are some of the environment factors. The next video we will be discussing on types of corrosion. Thank you.